the ground state eigen function for the potential that is given here, delta function potential, is given by the wave function is given. Okay, so the ground state wave function is given. A and alpha are constants, we are told, and there is a perturbation that is given, and we are asked to find the first order correction to the ground state energy. So the formula for the first order correction to the ground state energy is E1 is equal to, in terms of the Bray and the Ket notation, run the Ket notation we have, this is what we have to evaluate. So we have the ground state wave function multiplied or operated by the Hamiltonian, the perturbation. We have the perturbation function. Now that perturbation function, multiply it with your conjugate of your, the complex conjugate of your ground state function, and evaluate it between these limits. So what we have is, this is what we have. This is what we have, and since this is a symmetric function, so this is a symmetric function, so we can replace it by integration, doing twice the integration between 0 to infinity. And now when you integrate, when you do this integration, the answer that you get is, this is the answer that you get, 2 alpha cube. Now we have to find the value of A using the normalization condition of the wave function. So the normalization condition of the wave function says that psi multiplied by psi star integrated between 0 to, or minus infinity to infinity, should give you 1. Okay, so when you do this integral, so we again have, so you have to do this integral, so you can again, you can, this is a even function, so therefore I'm using this condition. So from here you can find out the value of, while doing this integral, we can find out the value of alpha A. So it turns out to be A square is alpha. So therefore we just substitute into that in our equation here, and we get that this is nothing but B times 2 alpha square. So this is our answer. So this option is given by option number D.